Inside a modern power grid, electricity does not flow in a smooth, single direction. It is an alternating current, physically surging back and forth dozens of times every second. To analyze and control this energy, engineers map these alternating forces over time. They plot the voltage on standard graphs, resulting in a sine wave. As circuits grow to support industrial loads, multiple signals overlap. Calculating these interactions requires tracking individual values at every point in time, which creates a significant computational load. To manage this complexity, engineers move away from time-based graphs toward a different representational system. This method involves a specific conceptual leap. Instead of tracking a signal as it travels across time, the entire wave is represented as a single rotating geometric object. This rotating object is called a phasor. By translating a time-varying electrical signal into a spinning vector, the calculus required to solve circuit problems is replaced by static geometry. This handwritten engineering document maps the mechanics of that translation. The rules laid out in this diagram provide the logic required to analyze alternating electrical systems. On the coordinate plane, we find the geometric foundation, a green vector labeled v sub m, pinned to the origin. It rotates counterclockwise. Its length corresponds to the maximum physical amplitude. Finally, the vector spins at a constant angular velocity, omega, matching the electrical signal's rate. These three properties, length, direction, and speed, capture a continuous sine wave within a single line. To apply this data, we need a method to translate it back into real-world physical values. If we freeze this rotation, we can determine the exact electrical voltage at that specific microsecond. Notice the dashed white line dropping from the vector's tip to the y-axis, identifying its vertical position. As the notes explain, this projection gives the instantaneous value. The vertical height represents the circuit's exact voltage at that split second. When set into motion, the y-axis projection rises and falls, tracing a sine wave outward through time. At 45 degrees, the projection aligns perfectly with the midpoint of the physical wave. When the vector points straight up at 90 degrees, the y-axis projection reaches its maximum, mapping to the peak voltage of the sine wave. When the vector lies flat at 180 degrees, the projection is zero, marking exactly when the physical wave crosses the zero voltage line. This demonstrates that the sine wave is a chronological representation of the rotating phasor. We now derive the algebraic expression from this geometric proof, written in the bottom right corner. On the left side, V represents the instantaneous voltage. On the right side, Vm serves as the hypotenuse of a right triangle. Multiplying that length by the sine of the angle isolates the vertical height on the y-axis. This expression establishes the link between a specific moment in time and the physical voltage value. This calculation becomes useful analyzing real-world circuits, such as an alternating voltage applied to a resistor. To understand this circuit, we must track a second force, current. This second document shows how both forces are modeled together. On the coordinate plane, a shorter white vector labeled Im represents the peak amplitude of the electrical current. In a resistor, the voltage and current vectors are collinear. They share the same rotational angle and point in the same direction. This geometric relationship indicates that the two forces are in phase, meaning that are synchronized in time. The right-hand graph illustrates the physical result of this synchronization. As both vectors rotate, they trace overlapping sine waves for voltage and current. Reaching 180 degrees at the same moment, both waves cross the zero line simultaneously. At 90 degrees, they both reach their maximum physical amplitudes. The equations at the bottom of the notes confirm this relationship. Both forces follow the same sign calculation, differing only in their maximum amplitude. By representing these complex interactions as spinning vectors, electrical engineers can definitively analyze volatile alternating currents as stable, predictable geometric relationships.